welcome everyone to the 11th Tech Talk, ALASCA Tech-Talk of the year. It's also the last talk of the year. We will have a Christmas break in December. I have the feeling it would be quite lonely if I tried to do a Tech Talk on the last Friday of December. So this is the last talk of the year, and then we can continue in January with new topics. So in case some of you are joining today for the first time, my name is Maria. I am with Cloud and Heat Technologies, which is one of the founding members of ALASCA, and I moderate these Tech Talks. And they are being recorded. You must have seen the message, and they will be uploaded in YouTube. So just that you are aware of that in case you ask any questions or if you share something here in the talk. As always, we have a quite brief agenda. We have a Tech Talk planned for today, which will be around 20-25 minutes. Then we will have a opportunity for questions and answers to today's speaker. And then we have some time at the end to share any events and news that you might have. So we always prepare some news that we think are interesting for the community or that are related to Alaska. But if you have anything that you want to share, the room is open to everyone, so just think about anything you might want to share, and there will be some time at the end for that too. So I will not take more time with Introduction. Let's start. Today we have Markus from Cyberus Technology, who will be doing today's Tech Talk. Markus was an engineering at FireEye, and then has had several positions at Cyberus, which he also co-founded, first as engineer, then as engineering manager, and now as director of engineering, so working a lot on virtualization topics. And he will be talking today about building a modern, secure, open hypervisor for the cloud. So he will be sharing some of the insights of Cyberus with building a secure hypervisor. And with this, whenever you're ready, Markus, I will stop sharing my slides, and then you can start sharing yours.
Okay. Is that working for you?
Yes, it's working.
All right, perfect. Yeah, then let's just jump right in. About the modern, secure, open hypervisor for the cloud. In order to do that, let me just help set the stage a little bit by talking about why are we talking about this in the first place, and that is basically what is the status quo and why is that a problem? If we look at the OpenStack landscape, one of the key things is that KVM QEMU is pretty much the de facto standard for OpenStack installations. So in the OpenStack user survey, I picked the one from 2022 here. You can see that the bars for KVM and QEMU are just basically the biggest together combined, make up pretty much all of the installations with just minor exceptions. It's not exactly representative, it's only a small sample size, but another supporting factor is that KVM is also configured as the default hypervisor for compute in OpenStack. And one thing that we can immediately see here is the weird sum of KVM and QEMU, which adds up to more than 100%. And we don't know exactly where that's coming from, but one thing that is important to remember is that sometimes we're talking about the split between hypervisors and VMMs. And that is the case here as well, that KVM is the hypervisor in the kernel, in the Linux kernel, and QEMU is the virtual machine monitor, which runs in Linux user space. And QEMU can be used standalone without KVM, but it's also the most common combination is KVM QEMU. So that's what we're largely talking about in this talk. And so with that said, there's a security analysis of KVM QEMU from 2017, which was performed by the BSI in Germany. And they looked at QEMU and KVM separately with the strong aspect of security in mind to see how well they're suitable for high security and medium security environments. And if we start with QEMU here, then there's one thing that stands out immediately, and that's that it's around 1 million lines of old C code, which is already, to start with, not the best basis for secure products anymore. And with all the security relevant compiler warnings enabled, which they did in their analysis, which is not the recommended way from the QEMU build process, interestingly, but it's something we highly recommend for any person who works with C and C++ code. They found pretty much around 16 compiler warnings per 1,000 lines of code. So they found quite a lot of warnings that are unaddressed. And these warnings comprise integer conversion errors, which make up the majority of these warnings, about 90% plus, but also things about missing initializers or pointer arithmetic, which sometimes can go wrong in these languages. And it's kind of a systemic issue they found, because with this number of warnings and also the reduced set of warnings that are even enabled in the recommended build process, it's likely that developers are not aware of these issues when they add code or modify code. And with this amount of warnings, it's kind of, it's not feasible to fully analyze all the problematic code sections in detail. So QEMU is, not exactly suitable for higher security requirements is basically the bottom line here. If we look at KVM instead as the basis, that is considered solid with some room for improvement. They found that there is good protection of security critical registers in the processor, but they also found that there's a sometimes unnecessarily large attack surface with things that you just cannot avoid having in the product if you build one. And that is, for example, the Hyper-V paravirtualization interface, and also things concerning the performance management unit. They also found issues with device pass-through, which is, of course, generally a problem. If you trust the hardware and pass it on to an untrusted guest, then you have to consider the implications of that. And there are specific devices that are designed for virtualization. They are using SRIV technology. And that, in combination with proper interrupt remapping and handling by the kernel, that is acceptable for normal security requirements, but they don't recommend using device pass-through for high security. There's one thing to mention here. This report is from 2017, so we definitely have to look at the ongoing improvements that went into the Linux kernel. But just as a little basis here, there's a solid base, but there's stuff to be done for higher security environments. And one other thing about the attack surface is also that what they didn't mention is that there's instruction emulation or decoding in the kernel going on in KVM, which can also sometimes be an attack vector, and that can gain you kernel rights in the end. So that's also something we want to look at. Another motivating factor is that especially kernel issues with virtualization are expensive to fix. It often requires you to reboot the machine, or at least have some minor downtime or degraded performance while you migrate around the VMs that are still running to free up the host to perform the updates. And that kind of creates a conflict of interest between the cost you have to spend to improve your security and actually improving the security. And the more of these fixes you have to deploy, the more expensive it becomes. So bottom line, if we can avoid having to having these fixes to deploy in the first place, then we have fewer problems and also fewer costs. So that's the goal. And then there's another aspect that is the certification effort, which is often a very tedious and manual process to get your product certified for certain security clearances. And that's usually not exactly the provider's core competence to provide this secure base platform and go through the entire certification process. So our goal is to provide an out-of-the-box certifiable virtualization solution that is based on KVM, which addresses the findings that this older report had, and that is also customizable to suit your needs as a provider. And we also provide the support to continue to provide your product. To provide a bit of history where we came from to this point where we are now is the Cyberus Secure Virtualization Platform, SVP, which we developed before. And in a nutshell, I'll try to keep it brief to save some time. We had a micro hypervisor, a microkernel-based architecture here with a Hedron hypervisor, which was based on Nova. developed at the TU Dresden here. And it then consisted of a pass-through Linux control VM, which pretty much had all the access to the hardware. And then with a modified user space and a minimal kernel module to run the virtual machines on top of this stack, which are kind of conceptually next to the control VM in that case. So we had some level of control over what is running in these VMs and how it's isolated. And we had the goal of minimizing all the amount of code that runs in ring 0, so in the privileged processor modes, which was achieved by the microkernel approach and by the very slim SLVM kernel module that you see there. So all the blue parts are privileged, and all the dark blue and all the light blue are deprivileged. What that enabled us to do is reduce the exposure to CVEs. So everything that was in this example as VirtualBox VMM, all the CVEs that affected the kernel part were basically out of the questions and did not need to be addressed because we replaced the VirtualBox kernel part with our code. And we also enabled extended kernel hardening in that case, which was GR security, which was not compatible with the VirtualBox kernel code at the time. And this SLVM kernel part in the control VM basically only handles a bit of memory management and then relays all the rest that is to be done to the user space in the microkernel part. That thing worked. It provided some good security features here, but we also faced some major challenges in doing all that. One big one being the hardware compatibility. So there's a nice little anecdote where we found a problem with a Samsung NVMe controller, which just vanished after some power setting changes. And it just showed us that whenever you're on the critical path as a hypervisor or a virtualization platform between the device drivers and the actual hardware, then things can go wrong. And Linux has a lot of quirks about these hardware specifics, but that just means that there are more of them. And sometimes we were just not able to address them properly. And we also played a lot of feature catch-up. We initially designed this for Intel x86. So we were missing ARM, AMD, RISC-V support. We were also missing nesting virtualization and efficient device pass-through with VFIO. And last but not least, also the security features by processors that happened in the last years, which is the TDX from Intel and the SEV from AMD. So the enhanced virtualization security features that came along, we also didn't have those. And another big thing is the performance in that case. So whenever we are on the critical path, which is, for example, interrupts, we incur a penalty here, and it's really difficult to make up for those and provide a good performing system in that case. One major thing would be the IOMMU, which handles or which controls device access from kernel drivers and also what the hardware can do. And controlling that from our virtualization layer was just a very big performance penalty that in the end we could not feasibly build into the product. So we gave the Linux control VM full control over the IOMMU. That's not to mean that this microkernel world is not useful. We still have some nice ideas around that, and we like the concepts, but for now, we just realized that building this system from scratch was just not a viable product in the end. So what we learned from these is that we want to provide better value with open source based solutions that are out there and in use and incrementally improve them, which we called Mission Apollo. We want to use evolution instead of revolution in that case. So basically saying KVM and the existing VMMs on top of it are not perfect, but they are pretty much an unavoidable part of the modern virtualization stacks out there. And replacing that with a completely custom one is just not feasible for us. And they have an extensive feature set and hardware compatibility. They are widely integrated. There's OpenStack integration available. And we just want to provide the Cyberus hypervisor in that case, which is a certifiable virtualization stack that is based on a minimized KVM solution. And on top of that, we also want to increase and intensify the whole quality assurance and testing story of these existing solutions. And to go a little bit more into theory now is how we want to improve the existing status quo. It makes sense to look at the rule of two attacker modeling that is based on Google's Chromium article. And it basically says whenever you have the combination of untrusted inputs that you process and also unsafe language, then you should have a sandbox, for example. So basically you have these three dangers, the unsafe language, the untrustworthy inputs, and the sandbox, or the lack thereof. And you should never have all three at once. That is the danger zone. And basically the last line of defense, if you have an unsandboxed processing of untrusted inputs, then you should definitely use a safe language with respect to memory. And if we now look at the attacker models that we came up with, the basic version is you gain kernel control in a virtual machine. So Windows, for example, is attacked and you gain kernel control, and you can attack the virtual machine monitor from there. And our goal is to provide integrity, availability, and the confidentiality of other virtual machines and the host in that case. Whereas an advanced attacker scenario might be that you actually breach the boundaries where you violate this rule of two. So you have some code that lives in this danger zone. And even in that case, we want to provide the integrity and the confidentiality of the virtual machines and the host in that case. Another way to look at these attack modeling things is to form attack trees, which is where you define your assets that you want to protect. In this case, we have secure processes or secure virtual machines, and the confidentiality and the integrity of those. And on the other end, at the bottom here, you have the attack vector. So that is what the attacker can control. You can assume a hostile network. You can also assume periphery devices that are hostile or taken over. And you can also assume the hostile guest, which is the example I want to use here. So if you have a hostile guest or an attacker in the guest, then you can first start to try and exploit the next boundary, which would be, for example, the VMM. So the virtual machine monitor provides device models, and you want to attack those to gain access to the Linux user space. In that case, if you happen to encounter a sandbox, you also have to break out of this one first. And then you exploit the kernel. And then in the end, if you compromise the integrity of the Linux kernel, then you can actually attack the assets and you have control. And basically, this is just a nice list of lines of defense that you can make up. And basically, you want more boxes anywhere, everywhere. So the more boxes you have, the harder it gets to actually get to the assets. And one way we look at it is to find places where there are not enough boxes and either harden them or add more boxes in. So when we try to secure the Linux kernel, one thing we definitely want to do or are in the process of doing is minimizing the attack surface. So whatever is unnecessary in the scenarios we look at, we want to make it configurable so it's not in the trusted compute base if it doesn't have to be. We also want to improve the use of the language in this project, which would be to introduce Rust at critical points. And then, as I mentioned before, we also want to improve the quality assurance by adding fuzzing and static analysis tools to improve the attack surfaces that are still remaining. Another aspect could be to move critical workloads that you have in the kernel into virtual machines to just add another layer in that case. And then last but not least, we can also think about hypervisor-based protection mechanisms. I'll come to that a bit later. Yeah, one thing that one of the unnecessary attack surfaces we want to attack is the Hyper-V part that was mentioned in the report. Also the instruction decoding and emulation and the virtualization of interrupt handling. So whenever we can remove part of those from the equation, we can be sure that this code is not the problem. And one way we want to do that is by using RVM kernel module, what we call it. It's a research vehicle we use for rapid prototyping. It's basically a very minimal kernel module again, but without the microkernel part underneath. And it just does the bare essentials of virtualization code. Everything else is done by the user space VMM. And what this enables us is to have a very nice small playground where we can play around with Rust and also other hardening techniques. And our goal is to feed all those results back into the actual KVM development to improve KVM in place. And we would like to do that in an open fashion. So the RVM will be at some point available on GitHub to create some form of collaborative research effort here. Now, I mentioned the hypervisor-based protection mechanisms, and one of them we already prototyped in a research effort, which tackled the CVE mentioned here, which was basically a use after free bug in the Linux kernel, which allowed you to escalate your privileges to root. And in our prototype, what we did is we protected the credentials data structure in the Linux kernel, which was attacked by this CVE case. And after the kernel enabled the protection by calling into the hypervisor, we protected these credentials by marking a read-only in the nested page tables, and thereby are able to catch the modifications that are not intended by the kernel. And this is basically sort of a collection of mechanisms that Microsoft already is pioneering with their virtualization-based security, which is just leveraging the virtualization properties for advanced OS protection. If we go up from the kernel into the user space, we also want to have a secure VMM. And basically, QEMU, we already talked about it, is it's a lot of code, and it's old code, and it's C code. So we don't really see the point in trying to improve the situation there. We would rather build on something modern, which in this case would be the cloud hypervisor written in Rust. And with our improved version of that, or curated version of that, we call Particle, we want a minimal feature set that has backends for our research prototype RVM, and it already has the KVM and Hyper-V backends. And by integrating this cloud hypervisor basis better into existing solutions, adding testing and quality assurance, and also some missing features. One example that comes to mind could be the live migration to other hosts, which it currently doesn't have. We can, together with a hardened KVM, really provide a round and open source good solution for modern cloud stacks. Now, going a bit more into the researchy area here, we could also think about adding virtual machine introspection in the user space, where the hypervisor just provides some hooking mechanisms, and the guest monitor implements the hooking logic that then inspects and logs calls that are made that are interesting. It can also return results that are not real, so spoofing. And the tooling that does this is safely isolated from the malicious code that is running inside the guest here, because it's running outside. And we've already built a research prototype of this to trap syscalls that are made in Windows and analyze them and also find problems with it. And another version of this would be the hypervisor-based endpoint detection and response, which is part of a research project we are doing with the Westfälische Hochschule in Gelsenkirchen, where we plan to protect these EDR systems from evasion by the attacker in the guest. And we do that by also monitoring certain things in the guest and then detect and prevent the guest kernel takeover. This is still in the early phases of the research project. I added a link in the end on a reference slide, just in case you're interested. But this is definitely a very interesting field for us to be in. So to summarize this, we are currently actively pursuing improvements of the security in the KVM space and pair that increasingly secure KVM version with safe virtual machine monitors. We are planning to work with the open source community in this case and make it in the open. and also contribute substantial quality assurance capabilities in the form of test automation and, yeah, as mentioned, fuzzing and static analysis pieces. And we are, of course, happy to talk to anyone who's interested about this. So feel free to reach out to me or to Florian, who's also in the call here, if you like to talk about this more. And just for the recording, I just show the references slide a little bit while you can think about if you have some questions for me. Thank you.
Thank you very much, Markus. So are there any questions from the audience? If you have any questions, you can just raise your hand or unmute yourself and ask the question or paste it in the chat. Okay, so maybe I don't see any questions right now. Maybe a question from my side. So you were talking about the RVM as a vehicle for research. So does this mean that it can only be used for research purposes, or is it also a component that could be integrated into a real cloud infrastructure?
Currently, we don't really see that on the horizon because it carries most of the problems we've talked about with feature catch-up, performance penalties, and all these things. So we really see it as a research vehicle that allows us to test new methods or new technologies in an isolated space without having to rewrite the entire kernel. So if we think about, for example, the Rust part, if we manage to create a kernel module that does all the virtualization critical things in Rust, we can do that very nicely isolated in this RVM context. It would be much harder to do this easily in the KVM current code base.
Okay, thanks. Any other questions? I need to scroll through all the participants to see if any raised hands are here. No questions. Okay, so then maybe another question from my side. You also mentioned that you're sort of feedbacking the research in the RVM to the KVM. What does this exactly, how does this work? Maybe do you have like an example or the kinds of things that you're feedbacking back to the KVM, or so that we can better understand?
I mean, one aspect I already mentioned, which is the Rust part. So whatever can be written easily and nicely in Rust, we could try to contribute back to the kernel whenever it's ready. Another part would be the minimization. So if we can use RVM to prove that a certain minimal version is viable as a standalone part of KVM, then we could try to recreate the same minimization on the KVM side directly, so it's useful for everyone.
Okay, thanks. There's another question in the chat. When will this stack be production ready?
That's a good question. We are currently targeting, I'd say, first half of next year. Florian, correct me if I'm wrong.
No, first half of next year is a good target, yes.
Okay, thanks. Another question in the chat. Does in-kernel Rust provide enough features for your current use case?
As far as I know, it's not quite there yet. It's getting there. I might relay that question a little bit to Julian, who has more experience with the nitty-gritty details of Rust in Linux. But as far as I know, it's getting close, but we also haven't tried yet to fully use it in the context we are looking at.
There should be everything there, but we're not quite sure. I think for that we have to progress a bit more.
And another question, if not, in which language is RVM written now? C?
Our current version of the ARM prototype is C, exactly, yes. And we are looking at moving that to Rust as soon as possible. And also, of course, all the Linux kernel part is currently C. But yeah, at the time where we started building RVM, I'm pretty sure that the Rust support in Linux wasn't quite ready, at least in the versions we were looking at. But yeah, with the new year comes new, fresh energy to tackle the Rust part.
Another question in the chat, I will just read it out loud. Have you thought about using AI to help with certain topics?
I'm sure we joked about it, but I think beyond the part of letting ChatGPT write some abstracts and fixing them afterwards, I don't think we've really seriously considered it, no.
Okay.
Well, maybe this is Tor here. Maybe it's fair to ask the question back to Jan. What's the background for the questions? Do you have inspiration for us, ideas how one might use IA in a, yeah, let's say productive fashion here?
Yeah, hello, Tor. Can you hear me?
Yep.
Yeah, thank you for your question. Not directly, I thought about and I tried to came up with some idea, but I mean just to use ChatGPT is to that's not the I guess not the right way, but I thought about to find some useful patterns to optimize some of your techniques you presented here. So that would be the more common case I thought of.
I mean, there's definitely one thing now that I look at the summary slide again, where in fuzzing and static analysis, we could definitely look at ways to improve on the pure random fuzzing, but more intelligent fuzzing maybe, and also come up with solutions to problems that were found. So there's at least a chance for some place to use these technologies when just randomness isn't enough.
Yeah, or maybe some kind of to try to secure your product somehow with more AI capabilities. But I don't know.
Yeah, that might be an interesting challenge to take up with the certification effort when you try to prove that these AI technologies actually do the protection they promise. That's already hard enough with actual code that you can understand.
Yeah.
Maybe an opportunity for a little experiment. You create two teams, one works with AI, one works without AI, and then at the end you compare the results, which one is more secure or better, more efficient.
Yeah. I kind of think of the better use for AI in the attacking side, in the pen testing and these elements, than to actually rely on it to provide the security. But I'm also happy to be proven wrong. So maybe we have ourselves a challenge here.
Great. So are there any additional questions? I think there's another one in the chat. What is your certification or accreditation target for your technology?
That's usually the Verschlusssache and then NFD and Geheim, I think, these targets. Florian, maybe you know some more details.
Yes, those are the ones.
Okay, and there is another question in the chat. How does the Cyberus solution compare to Firecracker?
I think that's one for Julian, right?
Can you hear me?
Yes.
So I think Firecracker is more intended for container workloads and function as a service, and I think we focus more on the general purpose virtualization.
Okay. So let's wait a couple of seconds in case there are any additional questions in the chat, which takes a little bit longer. I don't see any raised hands.
Well, let me do the same thing again. So, Robin, I thought your question was very interesting. Maybe you can, yeah, okay, not working. Yeah, well, we'll be very interesting in hearing more, on your views on Firecracker relative to what we're doing here, right? I mean, we're looking for feedback, of course. And the same thing, Michael H., ja, es ist eine sehr spannende Frage, was du da, sorry, a very interesting question, what you're asking. And we would be interested in hearing your experience also in this certification space. So, please use the opportunity, write us. I mean, we're very interested in following up on these questions and making our story and maybe your story more complete. So Robin, I understand that you have some connect issues, but yeah, please write us so we can understand your concerns, particularly around Firecracker versus what we've presented here.
So in case you don't have each other's email address, then just feel free to paste it in the chat here, and then you can get in touch with each other and continue the discussion with better audio quality. Okay. So you have Robin's email address in the chat, and yeah, I think in the slides from Markus there was also the email address to get in touch with Cyberus. Okay, great. So thank you very much for the presentation, Markus. Thank you very much to everyone also for the questions and the discussion. And I will just start sharing my slides again to share some of the news that I was mentioning before. Give me just 1 second. I have too many things open. Right. Okay, so now we have a couple of minutes to share some news. As I mentioned before, you can also share your news. This is just a summary of the ones that we have that we are aware of, but there might be, of course, other things that are interesting to the rest of the community. So first, an important thing for Alaska, there was a General Assembly last week. Actually, I didn't take part in this, didn't participate in this General Assembly, but I think we have Ariane in the call. I don't know if you would like to say something firsthand on the results of the Assembly and what went on last Friday.
Yes, 1 second. Okay. Yeah, I can share a little bit, maybe not a full recap because that would take too long, but yeah, I think one of the major outcomes of the General Assembly is what you actually have on the slide here is we are now welcoming 2 additional open source projects to the association, which is very amazing that we are doing this in 2023. It's a nice way to end this year. And this is on the one hand, YAEG, yet another Kubernetes engine. You've heard about this in our Tech Talk number 9. This is a project that was initially started by 23 Technologies. And then we also have Krake, which is our workload orchestrator that was initially started by Cloud and Heat. We heard about that in July of this year. And yes, we are very, very happy to be welcoming those 2 projects. It's very nice because we started with YAUK and now it's not just 1, but 2 additional projects. And then aside of that, we talked a lot. Of course, we looked back at the first year of ALASCA, which was also very great. A lot of cool stuff happened. We looked into the future, what 2024 will bring, and there's a lot of great things on the pipeline for sure. And then we also further developed the governance model of ALASCA and discussed how we can integrate new open source projects into the association. Yeah, that's basically it, I would say. And no, it was a really, really good year. Also with the Tech Talks, it's cool to see how far we've come with that. That would be my mini recap of the assembly.
Yeah, and let us not forget that I think ALASCA was mentioned in the Bundes community from the Bundeskanzleramt, right? So at least Mario sent out a little snippet of a film where ALASCA was mentioned in that context. So I think after 1 year, I think we're the public relations part, I think you guys are doing a really, really good job at that. And I think we should acknowledge that you guys have taken us a long way this year. And we are very much appreciative of that. Ariane, Maria, and the rest of the team leading this. So thank you very much.
Thank you. It's easy when you have a very nice community, I have to say that. So the enthusiasm of the members is very motivating all the time. So it's a lot of fun.
Yes, thank you very much, Ariane, for your summary. And it's great to see that that we are progressing very much with ALASCA, and that this nice feedback from the community. So yeah, let's keep the work. Okay, so maybe also just brief mention. I think we presented we mentioned that there would be a sovereign cloud stack community hackathon taking place in Dresden at the beginning of November. And it was supported by ALASCA. It was, I wasn't in the hackathon either, unfortunately, but I heard that it was a great success. So there was a lot of work from different groups discussing how the sovereign cloud stack can continue developing from both in a technical perspective, but also organizationally and so on. So I heard this was a great success. And here you see a little picture of of the group discussing and working together to continue developing the sovereign cloud stack. Then I also wanted to share some information with you that might be interesting. So also related to the sovereign cloud stack. So there's a standardization group that has been working on different things, and one of them is the process for cloud providers to apply for a sovereign cloud stack certification so that their services can be certified as SCS compliant, both for infrastructure as a service as well as for Kubernetes as a service. And so now they have a draft on regulations, and they want to collect feedback from the overall community. So there are some links here that let me see if I can paste it in the chat so that it's easier for you. So the first link is a link to the draft that has been prepared, and the second link is where you can provide your comments. So if you have time and interested in that, then just that's open now for commenting. If you have any questions, you can also contact our colleague from Cloud and Heat, Matthias, who is involved in this feedback collection process, or just send it to me and I will send it to him afterwards. But just an opportunity to provide some feedback on that. And the last point that I have here today is just a brief overview of the next Tech Talks. As I mentioned before, in December, we will not have a Tech Talk, so there will be a Christmas break. And then we start again on the 26th of January. It's always the last Friday of the month. at 11. And in January, we have a topic by DITIP, who will be presenting their open source multi-cloud resource management console. And then on the 23rd of February, we have a presentation by Fraunhofer. They will be talking about Clouditor, which is an open source tool that they have for continuous cloud assurance. So those are the next tech talks that we have planned for 2024. And maybe just a little warning, in March, there is an exception, so the Tech Talk will not be in the last Friday, on the last Friday of the month, but the week before, because there's Easter holiday. So instead of having an Easter break, we just move it 1 week so that we can meet again in March. So with this, I would be that would be my last point in the news and event section. I don't know if there's anything else from any of you, any event that you would think would be interesting for others, or any news that you've heard about that you would want to share. If so, please do so. Doesn't seem to be the case, I think. Okay, so just the information that I always share with you. Take a look at our website to know what's coming up in the next Tech Talks. If you want us to send you the calendar invitation, then subscribe to the mailing list. And as always, you can watch past Tech Talks on YouTube, the ones that Ariana mentioned, for example, on the new projects of the association, but also any of the Tech Talks that we've had last year. So there's been quite a few, and a very interesting topic. So they are all available on YouTube. If you have time and interest and you missed some of them, then take a look at that. And otherwise, we will meet again on the 26th of January. As I said before, it will be DITIP with the resource management console. And with this, we're done for today. I hope that you have a great holiday soon. And yeah, see you next year. Thank you very much to our speaker, and thank you very much to the rest of you for being here today, for discussing, for sharing your ideas. Yeah.
Yeah, thanks from my side too for the kind audience.
Yeah. So have a nice end of year, good start in 2024, and see you soon.